All right, welcome everybody to our last live stream for PHYS 251RI, Computational Research Methods in Physics. This has been a fun little pandemic-induced experiment with teaching this class online. Might try to incorporate some elements of this in future versions of the course. Don't know yet. Need to evaluate that. We have at this point basically discussed everything that we need to for the semester. And I've had people turning in their last couple of assignments, the final assignment and the final project. And so what I'd like to do today is do a special topic on Montecarlo integration. We talked about this briefly, I think shortly before spring break in class. I had you read about it. We didn't really do much with it in class, so I'd like to just kind of go over with it, and I'd like to do this a little bit differently. I want to build with you a Monte Carlo integrator. So I'm going to be building a code more or less from scratch. I already have a couple of lines in to help me learn a new, or keep track of a new library that I've imported. But other than that, we are going to build this code together. So that'll be a fun little way to wrap up the course, I think. So the idea of Monte Carlo integration, right? So let's just take one-dimensional example first. Let's suppose you're integrating a function. Let's say you're going from A to B, right? Here's my function. Here I'm integrating from A to B. Let's suppose this f, this is a particularly weird function. Let's suppose you graph this function and it does some really weird things, right? Maybe it does some frillies, maybe it goes down a little bit, maybe it, kind of loops around on itself. And it ends up looking kind of monstrous, right? Or maybe you've got your function from some data and you don't have a closed form expression for it, right? The way Monte Carlo integration works is kind of ridiculously simple. Here's the picture you want to have in mind. The first thing we're going to do, we're going to keep in mind this graph of our function. We're going to put a box around the function. All right, and this box needs to encompass our entire range of integration. So we're going to go from x equals a on the left to x equals b in the middle. So we're looking at integrating, getting all this area under the curve from x equals a to x equals b. Here's what you do with Monte Carlo integration. You choose a whole bunch of random points. You can think of this as kind of being like throwing darts at the box here. So just ignore the function for a second. We're just going to pick random points inside the box. So I might pick a point here, 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 pick a point here. And you do this a whole lot of times. You do this 1,000 times, 1,000,000 times, a quintillion times. However much time you have to run your code, you just have it pick random points. I'm not doing anything with the function yet. I'm just selecting random points. You can think of this as like throwing darts. You can think of it as like rolling dice. It's kind of like gambling, which is why it's called the Monte Carlo method. And here's what ends up happening. If you take the number of points that end up below the function, right? So that's going to be this point here. That's going to be this point here. That's going to be this point here. And divide it by the total number of points, right? So you're taking the fraction that falls below, divide by the fraction of the points that fall below over the total number of points. If you multiply that by the area of the box, right? Area of the box is just length times height. Right, so it's just going to be b minus a times the maximum of whatever the box is here. That's going to equal your integral, right? So call this integral I for convenience. This integral, all you have to do is calculate this fraction. That's it. It's kind of ridiculously simple how this thing works out, right? I mean, you just the most important thing you have to do is figure out what the maximum of that function is going to be. Place your box that high, and that's it. That's as high as that. That's all you have to do. The reason we don't do this all the time is because it converges very slowly, but it's guaranteed to give you an answer, right? I mean, as long as you can fit your function inside a box like this, it's guaranteed to give you an answer. It's really awesome. And so what I'd like to do today is build a code with you that carries out this integration. Now, I have a problem in mind that we'll look at, but let's take a look at implementing the method first. So the first thing we'll need to figure out how to do is how to generate random points. So I've already identified a function that will do that for us. So here I've imported NumPy, so we're going to use the NumPy library here. So we're going to have a list of points here. This points here is going to be a list. This is going to be our list of random points, or values for x. Hold on one second. Yeah, I ain't giving her anything. No. Okay, sorry about that. Let's see. So we've got, this is going to be a list of random points. Basically, the points are going to fall between the left value and the right value, and it's going to generate this many points here. And so just to test this, because you always want to make sure this thing is doing what you expect it to, you get this list of 100 random points. So we can generalize this, right? We can have our x minimum. Let's just pick a number here for now. Let's just call that maybe 0. We can have an x maximum. Let's call that maybe 1. And so this points list is going to go from x min to x max. Oh, and I need the number of x's. Let's go 1,000 for now. And I'll change this to nx. Cool. I'm going to take out this print points for now. We'll put it back in if we need it. Okay. So the next thing I need to do is start thinking about this box that I'm going to set up. So I need to have a y maximum for my box. Let's go ahead and let's see. So let's just go ahead and put a number for that right now. Let's just pick a number. It doesn't really matter what for right now. The next thing I'm going to need is my function that I'm going to be integrating. So let's define our function here. So how about we poll the audience? What function shall we try to integrate first? Let's pick something nice and simple. Let me know in the chat, what function would you like us to try integrating first? I haven't seen any responses from the chat yet. Why don't we pick something simple? Let's pick x. So let's say we were integrating y equals x. So we'll say return y here. We'll make this fancier a little bit later. Okay. So what I need to do now is to start working with these points. Basically, I need to count the points below and the points above. Now here's the thing though, I need to be selecting random points along the x and random points along the y. So let's try a list of x points and then a list of y points. So we'll do the same thing over here. Oops, sorry, not cut. Paste, there we go. We'll call this one y points. And we'll go from I suppose I need a y min as well, don't I? That might not necessarily be 0. We'll make it 0 just for just to make it easier on ourselves. So we're going to go from y min to y max and then same number of points here. I guess I could call that NP for number of points. List of random values for y. Save. Cool. And so now what I've got is a set of points in the set of values for x and a set of values for y. And so what I can do is just say for I in range 0 to NP. And now what I'm going to do is look at x and look at the x value and the y value for each of these. So here's what we're going to do. We're going to say that if, because we need to be able to tell whether a point is below the function or above the function at that particular x value. So I want to look at whether if y points of I is less than f of x points at I. Oops, excuse me. That was a control enter, not a regular enter. Then we need to add that to the number of points below, right? So we're going to call that in below. Needs to increase by 1. So I need to start with number below equals 0. I don't need to do anything if it's above, right? I'm just not adding to in below there. So then I'm ready to get out my integral value. Let's just consult our highly advanced equation over here. In below over in total times the area of the box. So we'll have in below divided by the number of points times the area of the box. So the area of the box is going to be x max minus x min times y max minus y min. And we'll say print integral just to be able to diagnose this. Make sure it works. I think I have defined everything I use. Let's find out. And there you go. We are taking the integral from 0 to 1 of x. Let's see. So the integral of that is 1/2 x squared. We're going from 0 to 1. So that should come out to be a half. And then we get a 0.502. So to within 2 digits, we've got this pretty accurately. And basically, if you want to make this more accurate, you just have to add more points. You might tack a 0 on here. Okay, well, it came out to 509 there. Let's try that again. 0.498. You can also do this a whole bunch of times and then average it. Another thing you can do to make it more accurate, you can lower Ymax, right? Because you can imagine if I make this ceiling higher, I'm going to get a whole lot more points above. And that doesn't really help my accuracy all that much. So what I could do would be to lower this. I suppose, I wonder if I can do this. Can I do y max equal to max of f of x points? I wonder if I can do that. And then we define f of x farther up. I wonder if that will work. Ooh, I think that did work. Can you print for me, please? Y max. I am learning Python with you here. Yes, that did work because we ended up with a 1 there, basically. All right, so that's pretty nifty. I can use that to just find out what the maximum value is. Yeah. Well, I might miss the actual maximum. I'll have to think about that, whether that works, because I am technically missing a little bit of data there. I don't know. We'll see. We'll leave it there for now. It looks fancy, so we'll do it. Okay, so what you can do now is you can change this to any function that you want. I can change this to sine of x and integrate from 0 to pi. Oh, I guess I need to also change this to be the minimum of these, don't I? Let's go minimum here. So we'll print y min, comma y max. So this, if we integrate sine 0 to 2 pi, excuse me, that should give you 0. Excuse me, np.pi. Oh, and this needs to be an np.sine, doesn't it? Let's see. This came out okay. Oh, okay. This is actually, this is only going to work if we set this, if we set a minimum of 0. Okay, so never mind. That's not going to work. We do want our minimum to be 0, actually. Just because the way we're calculating the area over here, we assume that everything is above the x-axis. I'm sure we could figure out a way to do that, but the application I have in mind is different than that. So why don't we try np.sine of x squared. And there we go. Yep, just about, what is that integral? I think, is that integral supposed to be pi? Because that looks close to pi. Let's double check that. Integral sine of x squared, comma x equals 0 to, let's take that as a suggestion. No? Okay, x equals 0 to 2 times pi. I think, yeah. Okay, yeah, that's supposed to come out to pi. And there you go. That's right about pi there. All right, cool. So we built that. We built that in about 10 minutes, basically. Like I said, Monte Carlo is extremely easy to do. But what I would like to do is turn this into a little bit more interesting physics problem. So if you've taken a quantum mechanics class, then you know that if you want to get the expectation value of something, right? If you want to get the average value of something, we'll just make it a gap for right now. You have to take the integral of the wave function times the thing times the wave function dx. And you got to go from minus infinity to infinity. So let's suppose, for example, you want to know the average of x squared, right? You need this in order to get the standard deviation in the thing's position. So you just sandwich an x squared in between here. If you're working with this thing called the infinite square well, where the particle has to be located somewhere between 0 and L. So it's not allowed to be out here, it's not allowed to be out here, but it is allowed to be in here. Then this thing turns into your psi inside this region here is square root 2 over L sine of n pi x over L. I promise that's an x there. There we go. And so this integral ends up being integral from 0 to L, because the particle is only inside the box, it's not outside the box, not to the left and it's not to the right. So you'll have a 2 over L from this thing getting squared. You'll have a sine squared n pi x over L, x squared dx. Let's see, does that have a closed form solution we can compare against? As soon as there's a trig function in an integral, I tend to turn to Wolfram alpha so that I don't have to do it myself. Okay, there is, it looks like a closed form integral there. Because by the time you add on an n pi in and over L, it just all kind of factors out. So we can use that as a comparison. But basically, you know what all this stuff is. You know pi, x is going to be the position along here, 0 is the length of the well. N here indicates your energy level. And so as you change your energy level, this integral should change as well. So let's suppose you go up to energy level 3. All right, now instead of being at 60, you're at 41. Let's suppose we increase this to 10. Oh, excuse me, we were at 41 before. Does this stay the same? I forget whether this cancels out at the end. Okay, it's changing a little bit. Okay, yeah. This number is changing a little bit. 4 pi cubed over 3 minus 8 minus pi over 8. Not exactly an answer I have memorized. And neither should you. That's what Wolfram alpha is for. Yeah, okay. This number does change a bit. Okay, so what I would like to do is carry out this integral and graph the results versus n. So here's the thing I have in mind. We're going to set up this thing to be that integrand. And we're going to loop over n and get out several different results. So let's take this whole thing, copy and paste it into a new cell. Because I've already got this working up here. I don't want to lose that. We won't need to import. Well, if we have to restart the kernel, yeah, let's leave import numpy there. Okay. All right, so our integrand. So the first thing I'm going to do is I'm going to kind of work my way from the inside out on this problem, right? Because this loop over n, that's kind of the last thing I want to add. I'm going to start here just by changing the integrand. So I need to make this 2 divided by L times, I've already got my sine of x squared, that was fortuitous, times x squared. And I have to change what's inside here, right? This has to be an n times pi times x over L, which means I need to define L up here. Let's just make it 1 for simplicity. This is going to be the well width. I suppose I could also do this versus L, but it's basically going to scale like a fraction over L. So that's not really going to matter too terribly much. So we'll set the well width up here. My x max now needs to be L, right? Because I'm integrating from 0 to L. This is my integrand that I wanted. Okay, I've got my Ymin here. I've got my Xmax. Excuse me, I've got my Ymax. I won't need to print these anymore. We already know that this is working. Okay. All right, and let's give this a try. So all I've done for right now is change the integrand. So let's see if we get the same answer as Wolfram alpha. Uh-oh, max of f of x points, n is... Oh, right. I have to define n as well, excuse me. Let's say n equals 1 for the energy level, and this has to be greater than or equal to 1. This is an integer n greater than or equal to 1. There we go. So I guess that makes it a counting number, I think is what you call those. All right, let's run that again. I got a 0.28. It's a little bit different than what I was getting over here. I think that's probably because we have the we don't have the pi in here. So I need n times pi times x over L. My sign is getting squared. My x is getting squared. Oh, and I need to have a 2 divided by L times this. And we'll go run. Oh, and this is not going 0 to 2 pi anymore. Right. This is going from 0 to 1 for x. 0.28267. Here we get a 0.28. That could be better, right? So this is where I know, this is how you get an idea of how many data points you need. You start out with a problem that you know the answer to. You compare it to the answer that it's supposed to be. And then you know that you need to make it more accurate. The way we control the accuracy is the number of points. 0.283, that's already better. Let's go ahead and make it one more 0. Now, of course, every time I do this, it's going to take 10 times longer to run because you're just running over the number of points. This is much better than 0.2828, 0.2827. Okay, I'm happy with that. So basically, you keep doing this until you are happy with the result. And now what I want to do is kind of get to the actual physics part, right? Because so far this is just an integral, right? This could be something that they throw at you in a math class. But when I start interpreting this as the energy level, then life is going to get interesting because this is going to be, interpreting some physics from it. So what I want to do is be able to go from n equals 1 to n equals 2 to n equals 3 to n equals 4, etc. So instead of having a static n value here, and you know what, let's copy and paste this into a new cell. So now instead of having a static n value, I want to have many n values. So I want n to equal, let's say, a range. Do I need a range? I think I just do range. Yeah, I think I just do range. We want it to go from 1 to, how high shall we go? Why don't we go up to 20? I think that will get me what I want. Print n, just to make sure that gives me what I want. No, that did not give me what I want. Okay, so we'll do np.arange 1 to 20 in units of 1. There we go. Okay, that's what I wanted. Oh, right. I have to go up to this because Python stops counting before the end point. Okay, so let's grab all this. So now what I can do, I can move all of this. So let's see. I want to take all the stuff that's going to be the same and move it outside the loop. For example, my y is possibly going to change based on n changing. So I need to keep that in the loop. But my x values, I can keep the same x values looping around. So I can start the loop up here and just say for... let's make this in list so that I can say for in list. And all of this stuff needs to be reset every time, right? So what I'm going to do is indent all of this. And so all I've done now is instead of having a static n value, I've added an n list and I put the stuff that changes each time inside the loop. The x values, they don't care what n is, so they can stay outside the loop, but the y values do care what n is, so they're going to go inside the loop. And now when I run this, I should get 20 different printed values for my integral. And I'm going to have it print it before I do any graphing just to make sure that those are coming out all right. Okay, that stayed the same. That's good. It's always nice when the math doesn't change. All right, let's try, can we get a 0.32 for n equals 2 over here in Wolfram alpha. So here's n. The only thing we're changing is n there. 0.32, there we go. Okay, can I get a 0.328 for n equals 3? 0.328, how about that? This is looking like it's working. 1, 2, 3, 4. All right, can I get a 0.33 for n equals 4? Sure enough, a 0.33. All right, I think this is working. I do believe this is working. That's always exciting when your code actually works. All right, I think we can stop this from running now. This is giving me what I want. And now what I want to do, I want to be able to visualize this. So I want to be able to create a graph of this versus n. So here's what we'll do. We'll say import matplotlib.pyplot as plt. I think that's the standard nomenclature. And now what I want to do, instead of printing these out, now what I need to do is add these integral values to a list, right? So let's call those x squared. Oh, no, wait, that's not going to work, is it? X squared dot append integral. And now I need to go up and define, oops, I need to go up and define x squared. So it's always safe to just start this as an empty list. Okay. And then what we'll do plt.plot in list, comma, x squared. I guess I could have called that x squared list to be consistent, but that is a bit of overkill, I feel like. All right, let's, and then I think you have to do plt.show, something like that. I'm sure it'll tell me when I do it wrong. Okay, so this is going to take a minute to run. Let's review what we've done here. So we've set our well width up here. That's another thing you could change. If you wanted to graph this versus L, you could do a loop over L as well. Here I've made my list of n values. This is the thing that I want to loop over, the thing that I want to graph again. So I have to make a loop for that. We defined our function that we wanted to integrate over. You can change this to any, any integrand that you want. If you're doing quantum mechanics, you can make this the wave function for the harmonic oscillator. You can change this operator. If you wanted to do momentum, you've got to do the wave function and then the wave function's derivative. Here I've got my list of x values. Again, we're just picking those randomly. Excuse me, never mind. Sorry, I got myself confused there. I was thinking this was, I had this out of order. This is x points, not y points. Then I start my list, and I'm just looping over the values of n in n list. So we're going up the energy levels. We are getting our y points. Those have to change each time because this function is changing, because this n value is changing in here. We are counting our number of points below. We're doing that with an if block here. And so I've got this loop inside of this loop. So for every new value of n, I've got to start over with my integral value, right? Because I want to get 20 integral values out. And then here I'm just calculating my integral using the very basic Montecarlo formula for the integral. And here I'm appending my current value of the integral to the list of x squared. And then I'm going to plot my result versus the physical thing that is changing the energy level. So it's going to show me is what is the value of expectation value of x squared versus the energy level. All right, while we wait for that, let's, just for my students, take a quick little look at what our schedule looks like for the last week of the semester. Where is that folder? There it is. Okay. So we will not have a live stream next week. Since we have talked about everything we need to talk about, I want to make sure you have time to work on your final assignment and final project. Also, I've got something like 4 different presentation slots scheduled for my other classes, so I will be a bit occupied in terms of my online time next week. But what I have done is offered an extra office hour next week. So I've shifted the office hours a little bit. So on Monday, April 13th, I'll have an office hour from 12 to 1. Then on Wednesday, April 15th, I'll have an office hour from 10 to 11. As usual, I will send you via email the link to that office hour just before we get started. I think I managed to send those ahead of time, but just in case, I'll send you the link a few minutes before we get started. Also, as a reminder, those last 2 class assignments, the final assignment and the final project, are due at 10 a.m. on April 20th. If you need an extension, or if you need any additional assistance or support, or if you need to just do an alternative assignment or something, please email me. I am happy to discuss that. I know we've all got family members that we're worried about. I know we're all struggling with going to the grocery store once a week. I have to go to the grocery store after class is over today. I mean, I have to get my list together. I have to find a mask somewhere. If all of that is making it is bumping this class down on your priority list, I totally understand. Just email me to let me know, what kind of accommodation you need, and we can work that out. This is not going to be the semester where I nitpick everybody's grade. That's not going to happen. Oh, joy. And of course, as usual, it tells me that it's prepared a figure, but it doesn't actually show me the figure. So let's do this. Let's try doing plt.plot xlist comma x squared, or nlist comma x squared. If anybody knows how to fix this, where it will actually show the plot instead of just a little piece of feedback, please let me know. That would be, my students and I would appreciate that. All right, and here we go. So when I'm looking at this graph, I'm trying to interpret this physically. So this is the expectation value of x squared versus the energy level. So this is going up in energy. This is going up in terms of what the square of the thing's position is likely to be. So the first thing I notice is that it's got a general trend of increasing, but it kind of levels off, right? And so it's like it's saturating around some value here, right around 1/3. I wonder if 1/3 is a magical value, or maybe it's some factor of pi or something like that. Let's see, what do we get if we put in really high in here? Because this can give me the exact result. Okay, that's going up to, okay, it's okay, so it looks like it's going up to 1/3 minus some ridiculous number that probably depends on n squared over pi squared. So yeah, I think this is supposed to be approaching 1/3. It looks like this is supposed to be approaching 1/3, which is kind of cool, right? That there's this, 3 is somehow important to this problem. I see that it increases. I also see that it wiggles a little bit over here, but you can kind of see that this wiggling it looks a little bit random. It looks like it's a little bit noisy. And that's where you have to remember that we're doing this random number approximation, right? That we're picking random points. And so depending on the points that got randomly chosen, these will fall a little bit below or a little bit above the actual result, which is supposed to be 1/3, and we do see it hovering around 1/3. So when I see noise like this, that tells me that I need to kind of ignore this up and down behavior. There's nothing significant. It's not that 10's value is actually less than 9's value, right? That's not actually happening. That's just noise in the data. So what I can do to improve that is use more data points. Now, of course, that's going to take longer than it did before. I don't want to make you sit through that. But that's what I would do with this to study it. All right, that's what I would do in order to get an idea of what is going on with this thing physically. So there you go. There's a little bit of information about Monte Carlo. So we were able to create a nifty quantum mechanics Monte Carlo thing in 40 lines or less. I'll make this available in our class folder so that you can play around with it, but I hope that's useful to you. Thank you all so much for participating in this class. I know that for several of you this was an elective, and it always delights me to see engineering majors and CS majors and even physics majors who already have the requirement who just want to take a class for fun. It always delights me to see students taking physics classes voluntarily. Yeah, that's just that really touches me, and I hope this is useful to you. And I'm looking forward to getting those last couple of assignments from you. So thank you all so much for your time and attention during this semester. I wish you the best as the semester wraps up, and I will see you in office hours next week. Have a great day. Bye-bye.